Hello everybody. This video is a quick review of chapter 4, probability, and we will start with basic rules. Okay, so the first thing is we'll talk a little bit about notation. If we have an event A, we say that the probability of A happening is P of A. Okay, and what do we say probability is? It's a chance of something happening. We say that the probability of any event is between 0 and 1, and it seems simple, but every semester whenever I have a statistics class, I have at least 2 or 3 people at some point telling me that they got a probability, let's say 2.5. Okay, that cannot happen, and we'll discuss why this happens and how to avoid this very common mistake. Okay, the closer probability is to 0, the more unlikely the event is to happen, and then the closer it is to 1, that means event is more likely to happen, right? And then if you have a collection of all possibilities for an experiment and you add up all of the probabilities, this must add up to 1. Okay, so there is a convention that we're going to use throughout this course, and you're going to see it again and again, that if the probability is less than or equal to 0.05 or 5% chance happening, then this event is unusual. So every time you see a question asking, is this event going to be unusual, you need to think, okay, I need to find the probability and compare it to 0.05. Okay, if it's less than or equal to, it's unusual, otherwise not so much. So let's say we have an example here. In a college of 5,000 students, 150 are math major. If I were to select one student at random and he or she is math major, would that be unusual? Okay, so let's see, how would I do this? Okay, so I would go probability of math major is what? Well, let's see. There's 150 math majors here out of 5,000. Then this should give me 0.03, so 3% chance happening. That's less than 0.05. Yes, this is unusual. Okay. So this type of question, is an event unusual, will come up again and again, and that's all you gotta do. You just need to compute this probability, compare it to 0.05, make a conclusion. Okay, so these are your basic rules, and let's get going. The next concept that we discussed was the general addition rule, and this rule applies when we have compound events. Okay, so whenever we're asked to find probability of event A or B happening, how do we deal with that? So the rule here is that we do probability of A plus the probability of B minus their intersection, meaning minus the probability that both of these two can happen. And this is the most common mistake that I see again and again. People forgetting this part right here. Okay, so let's go ahead and take a look at this example right here. We have a contingency table where we have right-handed and left-handed people, and then they're also classified as female and male. Okay, so there's 130 total students here. They go by gender and right-handed or left-handed. So let's say we have the following problem. If one person is randomly selected from the group, what is the probability this student is female or left-handed? Okay, so let's write it out and see what it looks like. Female or left-handed, probability that it's female or left-handed. Well, let's see. This is probability that it's female plus probability left-handed minus the probability that it's female and left-handed. Okay, so how many females are there? 71 total. How many left-handed people are there? 25. How many students are there that are both female and left-handed? 13. Okay? Minus 13. And then there's a total of 130. Okay? So let's see what happens. When I count all female and all left-handed people, I actually double count left-handed, and that's why we subtracted. Okay? So we do 71 plus 25. So let's see how much this is. 71 plus 25 minus 13. That's 83. Divide by 130. So that's approximately 0.6384. That's a pretty high chance. So again, what's the most common mistake that can happen here is not subtracting this part right here. Okay, gotta think about it. Can this happen both at the same time? Female and left-handed. Are there students that are both female and left-handed? And the answer is yes. How many? Well, let's see, 13 of them. Okay, so this is your general addition rule. Are there any situations when you don't have to worry about this one right here? Yes, whenever the two events cannot happen at the same time. So for example, what if you ask to find the probability of a student being, let's see, either right-handed or left-handed? Okay, then you just add up right-handed plus left-handed, right? There was no student that's both right-handed and left-handed. Okay, well, maybe they are, but let's just say they have to pick one or the other, right? So in this case, there is no probability. Well, there is probability. It's equal to 0. So whenever the events are disjoint, they cannot happen at the same time, male or female. Okay, that can't happen at the same time. That's the only time when you don't need to worry about it. Okay, so that's it. That's your general addition rule for compound events. Okay, so the next concept that we discuss was complements. Okay, and the complement is the opposite of an event. So for example, let's say my friend is expecting a baby and she would like to have a daughter. Well, the complement of that event, having a daughter, would be having a son. Okay, and what are the rules? The probabilities of two events that are complements must add up to 1. Okay, you either have one or the other. Okay, and then this rule right here is really the same thing as these two right here, right? So you just rearrange it. P of A is 1 minus P of A complement, and the other way around. Okay, so let's just take a look at one of these problems. You have a 52 card deck. What is the probability that you're not dealt a diamond? So let me go back up here and we'll do not a diamond. Let's say probability not diamond. Okay, I'm gonna say that it's 1 minus the probability of getting diamond. Okay, and this would be 1 minus, let's see, probability of getting diamond is, there's 13 out of 52, right? Okay, so if you do 1 minus 13 out of 52, what do we get? We get 3/4. Okay, does it make sense? Let's see, 75% chance happening. It makes sense because if you don't get diamond, you either get hearts or clubs or spades, right? So that's the other 3 options. Okay, now this example you say, well, that's easy. And the answer is yes. This is just a simple example of using a complement, but there are examples where it's so much easier to compute a probability event by doing 1 minus the complement. This one you don't really have to. This one you guys can just do it by common sense, right? So you say, wait, okay, if it's not diamond, then the other 3 suits are there, so that's 75% chance happening. Okay, but this is how you would use the complement rule. And let's see, let me think. I think the last problem on your activity 4 is dealing with cookies, right? So when you guys have a jar of cookies and different flavors, and I believe one of the parts needs to be done with a complement rule. Okay, so go back to that one and review that problem right there. Okay. The next concept in this chapter is conditional probability, and this one can be a little bit tricky. So here you have this formula that says probability of event A given that B happened is computed as follows. Probability of A and B divided by the probability of B. And these examples right here are pretty good examples to explain what happened here. So let's take a look at the first one. Again, let's go back to the example with cards. Find the probability that you got heart given that the card you were dealt is red. Okay, so let me go back here and write it out. So how would I write this example? Probability that it's heart and given that it's red. Okay, let's see, let's just think about it. If I were to find the probability that my card is hearts, I would say that's 13 out of 52. That's 1/4, right? Now this information right here, the fact that it's red changes a couple of things. So let's go back to the formula and see what it says. Probability of A and B. So how many cards are there that are both heart and red? 13 out of 52, right? That's the probability of heart and red. Okay, what is the probability then? Let's go back to the formula. Oops. Formula says probability of B, so that's probability of red. How many cards are there that are red? Well, there's 26 out of 52, right? So now once you reduce this all, okay, these cancel out, 13 out of 26, that gives you 1/2, okay? So this information, the fact that it's red, increases the probability that it's heart, right? So if you are not given the fact that it's red, you have only 1 out of 4 chance getting it. Now, not once I tell you that it's red, you say, wait a minute, but there's only half of the deck that's red. So 1/2, it makes sense that we get this one, okay? That's what the conditional probability is doing. Whenever you have given, okay, this extra information will either change the probability or sometimes it doesn't, and if it doesn't change, that means the events are independent. Okay, in this case they're not. So let's take a look at another example real quick. Let's see, what is the probability? It's a red card given that the card you were dealt is heart. Well, that one should be easy. Let's just think about it. If it goes the other way around, what is the probability that it's a red card given that it's heart? Okay, you should say, I don't need the formula. I know it's 100% chance happening, or probability is equal to 1. Let's see if the formula works. Okay, how many cards are there that are both red and hearts? Well, there's 13 out of 52, right? And then how many cards are there that are hearts? 13 out of 52. That's 1. And it makes sense, okay? If I tell you that my card is a heart, what's the chance of it being red? It's 100%, okay, or 1. So you can see that the order also matters. The given part is what changes your sample space, okay? So the given, this extra information changes your probability or your sample space, and thus the probability. Okay, so there's one video about conditional probability that I made recently, and I use example from Connect Math, and I go through a contingency table. So that one should be very helpful. Go back and watch this one video, and I'm using an example that's on your homework, just like it, might be slightly different numbers. Okay, so if you guys can do the contingency table problems, then you're all set. You're good to go. The next concept that we talked about was multiplication rule. Okay, so whenever you see that it's asking you to find the probability of event A and B, okay, so A and B, you know it's multiplication. So for or, whenever you see A or B, it's addition. If it's A and B, it's multiplication. And the general multiplication rule says that we do probability of B times probability of A, knowing that B already happened. Okay, a good example of this rule would be your problem with cookies, where you take one cookie out, right, out of the jar, and because you already know, let's say you took oatmeal raisin cookie, then the probability of getting an oatmeal raisin cookie again is no longer the same as it used to be, right? So if it was 10 out of 40, now it's 9 out of 39, because there's 9 cookies that are oatmeal raisin left in the jar with 39 cookies. Okay, so this is what we're really doing, and I have a video that goes through an example, I think with sodas, so go through that video again, make sure you understand everything, but we're really using this formula right here. Okay, so for events that are not independent, this is your rule right here. Okay, what if the events are independent? So let's see, let's go to the next slide. If the events are independent, that means that the occurrence of one does not affect the probability of another one happening, then you just have a probability of A times probability of B. Okay, if they're independent, you don't need to worry about the conditional probabilities because it's the same as before. And what would be a good example of this type of problem? Okay, let's see. What would I do? I'm running out of space here. Okay, so let's see. Let's do this. I have a daughter, female. Okay, what is the probability my next child will also be a daughter? Okay, oops. Here I am. Probability of female and female as my children. Okay, well, what was the chance of me getting a girl to begin with? It was 1/2. Okay, now, let's say I'm gonna get another baby in a couple of years. Well, since I already have a daughter, does it change the probability of getting a girl again? Well, Mother Nature says, I don't think so. You had one, you can have another 8, and they all can be girls, right? So 1/2. So the probability of getting a second baby is still, that's female, is still 1/2. Okay? The probability does not change. Just because you had one, it doesn't mean that the next one will be boy. Alright? And it works both ways, obviously. So the probability that I get 2 girls as my children is 1/4. Okay, so here's a quick example of events that are independent. Okay, in fact, I know someone whose family had 18 girls, then they had a 19th boy, and a couple more girls after that. Okay, so you can see that really the events are independent, the probabilities don't change, and this is how you compute it. Okay, let's see. So these are your main formulas for probability. Okay, I know we talked a little bit, your homework talked a little bit about, let's see, permutation and combinations, right? So talked a little bit about permutations and combinations. You guys go ahead and skip that. Okay, this is for your general education. It's good for you to see it. It's good for you to do a couple of problems online, but I will not test you on these things. Okay, so there is a difference between those two. If you've done your homework online, you're set. You will not need to see this in this class again. Okay, I think this is it for chapter 4. Thank you for watching.